You all there, let me be Junior back with some more reading and notes. You all there, let me be Junior back towards the reading and notes. You all there, let me be Junior back towards the reading and notes. You all there, let me be Junior back towards the reading and notes. You all there, let me be Junior back towards the reading and notes. You all there, let me be Junior back towards the some double audio coming through. Hello, y'all. Darrell Burry Jr. back with some more reading and notes. We'll do some thermodynamics today, heading towards the end of the semester. So as you can see, we're on chapter 6. And so I'll read through this first section, perhaps answer a few questions along the way. I actually have some homework problems to do in the sections that are coming up. I believe sections 6.1 and 6.2. I could look it up to be sure. But I'll see about I was coming back and doing some of those. I mean, not actually doing the homework problems tonight. Um, we'll see how it goes. So it looks like the ones I'll be doing, they're all from the textbook. It'll be, at least from this section, 6.2, 6.5, 6.6, and 6.10. So 4 from this section. So the idea now is to go ahead and read the text to get the background. And perhaps over the weekend, I'll read chapters 6 and 7 to get through the background of what's necessary to do the homework questions from chapter 6 and chapter 7. Most of it is from chapter 6. Looks like we're doing sections 6.1 through 6.6, but only section 7.1 and 7.2 in chapter 7. So we'll see how far we get over the weekend. So looking at the first part, I already read the first introductory part here, was talking about how the majority of the textbook up to chapter 5 was the second law of thermodynamics, which is dealing with statistical behavior of a large number of particles. We had applications in physics, chemistry, earth science, engineering, which uh, spoke about a bit before in problem solving. I did some problem solving a few weeks ago, I believe, and coupled with experimental measurements, we're able to get several predictions, like we did, I believe, the heat engines and refrigerators and things like that, utilizing uh, values that we get from experimentation. We also talked about models in the past as far as how we can apply thermodynamics to different systems, like a two-state paramagnet, which is basically a system of particles that have either a up or down inclination as far as their magnetism. They could either be aligned with a magnetic field or anti-aligned. The Einstein solid, in which we sort of treated a solid as a collection of oscillators of the same type. So you have a whole bunch of equivalent oscillators that are grouped together. And the monatomic ideal gas, which is a gas made of atoms that are not bonded. So like argon, the next example, that's the first one that comes to mind. There's a few others. And but before, we're able to get the multiplicity of the gas. So for instance, if you have a bit or byte, it's going to either be a 1 or a 0. So it's going to have a multiplicity of 2. You can have very complicated scenarios where, um, like with a paramagnet, depending on how many magnets you have grouped together, it'll be 2 to the n number for the multiplicity. So if you have 3, you'll have 8 multiplicity for that uh, paramagnet. And of course, Einstein's modulus gets even more complicated. Off the top of my head, if I remember right, the multiplicity was q plus 1 and q. If I remember right, that could be incorrect. But it's something like that, depending on the number of oscillators, the number of energy, and you add 1, and then basically use the binomial uh, choose something to calculate the multiplicity. But each of these, we had these simple combinatorics to get some way to get the multiplicity. But as we get into more complex models or systems, then combinatorics won't work. So now we're on to chapter 6, section 1, and we'll see what it's talking about. And again, it's a textbook, An Introduction to Thermodynamics by Daniel Schroeder. In this section, I will introduce the most powerful tool in all of statistical mechanics, an amazingly simple formula for the probability of finding a system in any particular microstate when that system is in thermal equilibrium with a reservoir at a specified temperature. All right, so we have a reservoir, for instance, the atmosphere. Then we have a small system, and a reservoir is at temperature T. So now we're not dealing with just a system. Like if you have just a paramagnet, and it's just a paramagnet by itself, we assume it to be isolated. Now we have, let's say, a paramagnetic that's connected to the atmosphere that they could exchange energy with. The system can be almost anything, but for definiteness, let's say it's a single atom. All right. So using this example, we have one atom here. The macrostates of the system then correspond to the various energy levels of the atom, although for a given energy level, there's often more than one independent state. And if you have any questions, you can ask in the live chat or in the comments later. So that's pretty much what I drew there. A reservoir, it has energy equals the energy of the reservoir, temperature equals T, and the system energy just equals E. And notice that the reservoir is at a defined temperature, not the system. And these two components can exchange energy. For instance, a hydrogen atom has only one ground state, neglecting spin, with energy negative 13.6 electron volts for a hydrogen atom, but it has 4 independent states with energy 3.4, 9 states with 1.5, and so on. Let's say and look at figure 6.2. So we have an S1 state, S2, and this is clearly 13.6 divided by 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. Must be 13.6 divided by 9. No, it doesn't seem to calculate. You have 9, and 9 times 5 is 45. That's 13.5. We're just about. Each of these independent states count as a separate microstate. When the energy level corresponds to more than one independent state, we say that level is degenerate. For a more precise definition of degeneracy and a more thorough discussion of the hydrogen atom, see Appendix A. If our atom was completely isolated from the rest of the universe, then this energy would be fixed, and all microstates with that energy will be equally probable. Now, however, we're interested in the situation where the atom is not isolated, but instead is exchanging energy with lots of other atoms, which form a large reservoir with a fixed temperature. In this case, the atom could conceivably be found in any of its microstates, but some will be more likely than others depending on their energies. Microstates with the same energy will have the same probability. So the 1.5 electron volts microstates will have the same probability. And it seems like they will be more probable than the others, I guess depending on the temperature of the reservoir. Energy level diagram for a hydrogen atom showing the 3 lowest energy levels. There are 4 independent states with energy 3.4 and 9 independent states with energy 1.5. So the 1.5 energy level seems to be 9 degenerate, the 3.4 3 degenerate, 3.4 is 4 degenerate, and the negative 13.6, which is the ground state, has no degeneracies. As the probability of finding the atom in any particular microstate depends on how many other microstates there are. I'll simplify the problem at first by looking only at the ratio of probabilities for 2 particular microstates of interest, such as those circled in 6.2. Let me call these states S1 and S2, their energies ES1 and ES2, and their probabilities PS1 and PS2. We're going to find a formula for the ratio of these probabilities. Let's go all the way back to the fundamental assumption of statistical mechanics. For an isolated system, all accessible microstates are equally probable. Things worth writing. Call this number omega r S1, the multiplicity of the reservoir when the atom is in state 1. Oh, did I skip? I can skip the one. Our atom is not an isolated system, but the atom and the reservoir together do make an isolated system, and we're equally likely to find this combined system in any of its accessible microstates. I think what he means is that so, we have a system that has a 4 degeneracy here and 1 here, each of these 5 macrostates are equally probable if the system is isolated. But since this macrostate has 4 macrostates in it, this macrostate will be more probable. So this energy was, let's say, 5 and this was 1. I guess I should say 15 and 5. The probability of finding the system in the 5 energy macro state is greater, but the probability of each of these macro states are equally likely. It's just that there's 4 in the 5 energy state. So it seems to be what's going on here. Now we don't care what the state of the reservoir is. We just want to know what state the atom is in. But if the atom is in state 1, then the reservoir will have some very large number of accessible states, all equally probable. I'll call this number omega R S1, which is all, I should just say the multiplicity of the reservoir when the atom is in state 1. So basically for that atom in state 1, the reservoir has the total number of macrostates it has that's equally accessible, though the macro state of any particular grouping of macrostates might be more probable. Similarly, I'll use as 2 the multiplicity of the reservoir when the atom is in state 2. So maybe I'll copy this down. These 2 multiplicities will generally be different because when the atom is in a lower energy state, the energy is left for the reservoir. More energy is left for the reservoir. The one thing that comes to mind is my understanding is the reservoir is basically assumed to be infinite. So, I mean, it's basically we're considering the reservoir is finite, and thus that energy from the energy difference of the system from being in one state or another does seem to make a difference in the reservoir. There's a glossary in here. Let's look up and be sure exactly what they mean by reservoir. Hey, what's going on, Duck? How you doing? Good to see you. So let me know if you have any questions if anything comes up, and I'll see if I can clarify. I'll go ahead and take a look and see if confirm that my understanding of a reservoir is fine. So I took a screenshot of where these pages were. So I thought I did. Let's see here. Try that one more time. Right, so we'll take a look here. I'll go to 122 first. And we would have to go to the heat engine for the first discussion of a reservoir. In general, a reservoir, so let's go ahead and write this down. Reservoir. In thermal, a reservoir is anything so large that its temperature, not its energy, its temperature doesn't change when there's a change in energy or a change in heat. And heat is basically energy. For a steam engine, the hot reservoir is a place where the fuel is burned and the cold reservoir is the surrounding environment. All right. So I was thinking it was energy, which was just throwing me off, but it's actually, temperature. The temperature doesn't change. It still seems kind of odd because the temperature is based upon energy. But we'll see where we end up. This textbook has been pretty good so far, so I just need to increase my understanding. And all right, it's probably better to just flip through. Up too far. All right. All right. So an atom is in a more lower energy state. More energy is left to the reservoir, so it does have more energy. It's just the temperature does not noticeably change. Suppose, for instance, that S1, which is the state 1 of the atom, has a lower energy, so that the multiplicity of S1 is greater than the multiplicity of S2, because we saw in the previous example that the lower the energy, the more the base energy is divided up amongst those states. So each individual state of lower energy, there's more of those than the states with higher energy. As a specific example, let's say that the multiplicity of the reservoir when the electron is in state 1. So let's say that the multiplicity of the reservoir when the electron is in state 1 or the atom is in state 1 is 100. And the multiplicity R when the electron is in state 2 is 50. Now, fundamentally, all microstates of the combined system are equally probable. All microstates of the combined system. Therefore, since there are twice as many states of the combined system when the atom is in state 1 than there is when the atom is in state 2, the former state must be twice as probable as the latter, and that's what I was covering earlier. So just extrapolating from previous thermodynamics that we did. Well, generally, the probability of finding the atom in any particular state is directly proportional to the number of the number of microstates that are accessible to the reservoir. Thus, the ratio of probabilities for any two states is all right, let's just roll with it. So P S2 over P S1 equals multiplicity of the reservoir when the atom is in state 2 divided by the multiplicity of the reservoir when the atom is in state 1. That's 6.1. Now we just have to get this expression into a more convenient form using some math and a bit of thermodynamics. First, I'll rewrite each multiplicity in terms of entropy using the standard definition. So we know from before that entropy is the Boltzmann constant times the natural log of the multiplicity. So this equals so what it's saying is that is the same thing as E ln that. Let's think here. Let's see. So we're doing E to the S equals E to the K ln omega. Right. Have S divided by K equals ln omega. Well, just bring me K to the other side, or divide both sides by K. So this means that E to the S over K equals E to the ln omega, which is sigma, which equals E I mean, not each of the sigma, but sigma. But that means that we can replace sigma with e to the s over k. We have p s1 over ps2 over ps1 equals e s sr s2 divided by k divided by e sr s1 divided by k. So basically I'm taking the sigma and substituting that. All right, so let's see what we have next. So okay, so it looks like they're just bringing that up to the numerator. We have e to the s of the entropy of the reservoir while the atom is in state 2 minus s of the entropy of the reservoir while the atom is in state 1, all divided by k, and this is 6.2. So the ratio of probabilities of the particle being in state 2 divided by the particle being in state 1 is the difference between the entropy of the reservoir while the particle is in state 2 minus the reservoir while the particle is in state 1. The exponent all divided by k, and then the exponent of the exponential. All right. Now we just have to get this expression into a more convenient form. We did that. The exponent now contains the change in the entropy of the reservoir when the atom undergoes a transition from state 1 to state 2. Okay, I'm going to see how it's state 1 to state 2. Usually we subtract the initial state. Let's see where it goes. The change will be tiny since the atom is so small compared to the reservoir. We can therefore invoke the thermodynamic identity. Infinitesimal change in entropy of the reservoir equals 1 divided by T. The change in energy of the reservoir plus P, the change in volume of the reservoir, minus the chemical equilibrium, I believe, BNR, I don't remember the exact name of that term, and it's 6.3. And this is the thermal ID. The right-hand side involves the changes in the reservoir's energy, volume, and number of particles. Okay. Where anything gained by the reservoir is lost by the atom. So we can write each of these changes as a minus the change in the same quantity for the atom. Okay, that makes sense. So it seems to say that the entropy of the change in entropy of the reservoir is mu dn of the atom minus du of the atom minus p dv the atom, which makes sense. The atom gets bigger, the surrounding environment must expand to accommodate it, which means it technically gets smaller. I'm going to throw away the PdV and UDN terms, but for different reasons. The quantity PdVr is usually non-zero, but much smaller than DUR and therefore negligible. The atom goes into an excited state, its effective volume increase by a cubic angstrom. So atmospheric pressure, the term PdV is of order 10 to the negative 25 joules. This is 1,000,000 times less than the typical change in the atom's energy of a few electron volts. Meanwhile, Dn really is zero, at least when the small system is a single atom, and also in the other cases that we'll consider in this chapter. In the following chapter, I'll put the Dn term back in order to deal with other types of systems. So the difference in entropies in equation 6.2 can be rewritten. So we have the change in the entropy of the reservoir while the atom is in state 2 minus the entropy of the reservoir while the atom is in state 1. And this is from the exponent of the exponential is 1 over T U R S2 minus U R S1, right? So you're saying only this is relevant, and that's going to be the change in the energy of the atom. So this is dus, the change in the energy of the atom. Okay, that makes sense. So then we have negative 1 over T E S2 minus E S1. And that's equation 6.4, where E is the energy of the atom. Okay. All right. We discussed how the whatever the electron gains, the uh, atom loses and vice versa. And actually, this is technically this energy of the reservoir, and this is this. So everything else is gone. We have just that. And now we have the change in energy of the system, which is E, because we discussed earlier that the energy of the system is just E. The energy of the reservoir is U. And the negative sign reverses the two, according to what I did here. And I'll call this 6.3.1. We're plugging this expression back into equation 6.2. So I'll write this one, then we'll stop here. We have the probability of system 2 divided by the probability of system 1 is going to be E to the entropy of the reservoir when the system is in state 2. Mine is the entropy of the reservoir when the system is in state 1, divided by K. So that's going to equal, when I substitute that, e to the negative es2 minus es1 divided by kt. Now I can distribute this. So this is e to the negative es2 over kt, e to the es1 over kt. So this is going to be e to the negative es2 over kt divided by e to the negative es1 over kt, which is what the book has. This is 6.5. This is the probability of the system being in state 2 divided by the probability of the system being in state 1. The ratio of probabilities is equal to a ratio of simple exponential factors, each of which is a function of the energy of the corresponding microstate that we get in the probability for and the temperature of the reservoir. Each of these exponential factors is called a Boltzmann factor, right? So now we know what the Boltzmann factor is. So the Boltzmann factor is the exponential of e to the minus es, energy of the state, divided by kt. So if you divide two Boltzmann factors, you get the probability, the ratio of probabilities of the states of the particle that correspond to the state of the energy. All right. And let's see how many pages we have. Looks like we just have just one more page. So I'll keep on going since the problem starts on the next page. Did I missed some problems already. So the problem starts on the next page. So let's finish this page here. It would be nice if we could just say that the probability of each state is equal to the corresponding Boltzmann factor. Unfortunately, this isn't true. To arrive at the correct statement, let's manipulate equation 6.5 to get everything involving S1 on one side and everything involving S2 on the other. So coming from here, we have the probability of state 2 divided by the Boltzmann factor for state 2 equals the probability of state 1 divided by the Boltzmann factor for state 1. And this is 6.7. Notice that the left side of the equation is independent of S1. Therefore, the right side must be as well. Similarly, since the right side is independent of S2, so is the left side. So the right side has S1, so I don't see how it could be independent of S1. But if both sides are independent of both S1 and S2, then in fact both sides must be equal to a constant. You'll have to be equal to a constant if they're different. For the same for all states, a constant is called 1 over z. It's a constant of proportionality that converts a Boltzmann factor into a probability. In conclusion, for any state S, all right. So what this means, if I want the probability, let's say, of S2, that will be E negative ES2 over KT divided by E negative ES1 divided by KT, all times the probability of S1, which is going to be YC. So this is, since both of those equal 1 over Z independently, we can do 1 over Z times E, so negative ES2 divided by KT, and that's 6.8. So this and this together equals this, which we got from the previous problem. You want the probability of S2, 1 over Z, times the Boltzmann factor for S2. And 1 over Z is the Boltzmann factor of S2 divided by S1 when it relates to state 2. So whatever one is you want, that one is in the numerator. And the other one is in the Z factor. This is the most useful formula in all of statistical mechanics. Memorize it. Right? So it says memorize this. This is the most useful formula in all of statistical mechanics. Memorize it. Equation 6.8 is sometimes called the Boltzmann distribution or the canonical distribution. To interpret equation 6.8, let's suppose for a moment that the ground state energy of our atom is E naught equals 0, while the excited states all have positive energies. Then the probability of the ground state is 1 over Z, okay, because it'll be e to the 0, and all other states have smaller probabilities. So it's divided by the Boltzmann's factor and its energy. Since with energies much less than KT, since states with energies much less than KT have probabilities only slightly less than 1 over Z, while states with energies much greater than KT have negligible probabilities. So let me write this. I'm not sure about this one. So the probability of E less than KT is greater than 1 over Z. and probability of states with energies much greater than AT less than 1 over Z, or negligible. This is just a little bit bigger. Figure 6.3 shows a bar graph probabilities for the states of a hypothetical system. Okay, so I had it in reverse earlier. The higher the energy, the lower no, I did have it right. The higher the energy, the lower the probability. But they just have it that I did have it reverse earlier. Because the smaller negative number is a lot more energy. So they are more probable because they have a greater multiplicity. So that makes sense. But what if the ground state energy is not zero? Physically, we should expect that shifting all the energies. Hold up. What if the ground state energy is not zero? Physically, we should expect that shifting all the energies by a constant has no effect on the probabilities, and indeed the probabilities are unchanged. If it's true that all the Boltzmann factors get multiplied by an additional factor of E naught over KT, it is true. We'll see in a moment that Z gets multiplied by the same factor, so it cancels out in equation 6.8. So I'm not clear on this one, but we'll see. Thus, the ground state still has the highest probability, and the remaining states have probabilities that are either a little less or a lot less. Okay, so I did have it right the first time. And the remaining states have probabilities that are either less or lot less, depending on how the energies as measured from the ground state compared to KT. All right, so I have to look at that again. And here's the bar graph of relative probabilities of the states of a hypothetical system. The horizontal axis is energy. The smooth curve represents the Boltzmann distribution, which is exponential. K, equation 6.8. For one particular temperature. At lower temperatures, it will fall off more suddenly, while at higher temperatures, it will fall off more gradually. All right. All right, so that's the first section. So perhaps what I'll do is work on some of the problems and come and share some of the problems. So look for me tomorrow to do some thermodynamics problems from this section, and then we'll continue through the first 6 sections. They may be all the sections, but the 6 sections of chapter 6, and then the first 2 of chapter 7. So see y'all next time.